Alright, now this is the section 2, or the free response question, part A. So the first part, there's 30 minutes and there's 2 problems. And you need a graphing calculator. So I have my graphing calculator here. Here you shouldn't be that limited on time, but you should still manage your time well. Uh, there's only 2 problems, and you have 30 minutes, but there's sub problems per problem. So you want to know, you want to manage your time. That's what I'm trying to say. Uh, you don't know how many before going into the test, but you still want to manage it well. So, so I'm timer for 30 minutes, and let's get started. All right, number 1. The temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where Wt is measured in degrees Fahrenheit and T is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of Wt at selected times t for the first 20 minutes are given in the table above. So part A, letter A. Use the data in the table to estimate W prime 12. Show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in the context of the problem. So, well, to estimate WT12, there's many ways we can do it. But one way we can do it is to just take the middle between 9 and 15, which is 12, and estimate it that way. So, if we, because that's like the closest bound, right? If we have a function here, we don't want to take, and we want to estimate the derivative here, we don't want to take these 2 points, right? Because this is very inaccurate. And instead, we want to take as close to this point as possible, which is more accurate of an estimate. So we can take between 9 and 15. So this is just basic rise over run. 67.9 minus 61.8 over 15 minus 9. And we can plug that into the calculator. So the numerator becomes 6.1, the denominator is 6. So it's approximately 1.01667. Sorry. Obviously you want to be writing more, so I'll do this after the problem. So using correct units, interpret the meaning of your answer in the context of the problem. Well, the units are Fahrenheit, degrees Fahrenheit per minutes. And what this means is it's the rate of change, excuse my bad handwriting, the rate of change of the temperature of the water in the tub at time t equals 12. So obviously this is a practice, so handwriting doesn't matter that much. If you're going into the real test, make sure your handwriting isn't as bad as mine. Take the extra time to make sure that the reader can actually grade it, because yeah, I'm just saying. I don't want to spend too much time on it. I'm just saying. Okay, part B. Use the data in the table to evaluate the integral from 0 to 20 of w prime t dt. Using correct units, interpret the meaning of this in the context of the problem. Okay, from the fundamental theorem of calculus, this is just w of 20 minus w of 0. So, yeah, I mean, so it's just 16 degrees Fahrenheit. Sorry, from FTC, this is equal to this. Degrees Fahrenheit, and that's not an R, that's an F. And the meaning of this is the change in temperature between times t equals 0 and t equals 20. Next problem. For T's between 0 and 20, the average temperature of the water in the tub is 1 over 20 of this. Use the left Riemann, I don't know, Riemann sum with the four subintervals indicating the data to approximate this value. Does this approximate overestimate or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. Okay. In the test, you don't need to scroll back and forth, which would be much better, but uh, I can write it down here, which I hopefully can see if I scroll down there. It's 0, 4, 9, 15, 20, 55, 57, 61.8, 67.9, and 71. Alright, I lied, I cannot see if I scroll down there. Okay, I can move this down here. Alright, sorry about that. Okay. So we can just use the left Riemann sum. So we have 4 times 57 minus 55 plus 5 times 61.8 minus 57 plus 6 times 67.9 minus 61.8 plus 5 times 71 minus 67.9. And we just plug this into the calculator. We have 4 times 57 minus 55 plus 5 times 61.8 minus 57 plus 6 times 67.9 minus 61.8 plus 5 times 71 minus 67.9. Alright, and that's 84.1, and it's 1 over 20 of all this, sorry. So divided by 20, which is equal to 4.205. Degrees Fahrenheit. So this this is certainly not right because I completely messed up my left Riemann sum. So the past 2 minutes, forget what I said. All right, don't 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 listen to what I said. Okay, let's do part C now. All right, so uh, I'm running low on time. I gotta hurry up. Sorry. 4 times 55. Okay, you guys know what I left from somewhere. So 5 times 57 plus 6 times 61.8 plus 5 times 67.9 divided by 20. So I gotta speed through this now. I'm sorry, but uh, I pretty much did this already. So um, this should be fine. But this is equal to uh, 60.765 degrees Fahrenheit, right? So this and this uh, underestimates because this is increasing, so it looks something like this. And we're taking the left sum, so it looks something like this. So there's always this gap here that we don't have. So it's underestimating since WT is increasing on the interval between 0 t 20. All right, part D. For t is between 20 and 25, the function w, the models of water temperature, has first derivative given by this. Based on the model, what is the temperature of water at time t equals 25? All right. The fundamental theorem of calculus, the difference in water temperature between 20 and 25 is just the integral from 20 to 25 of w prime t dt. So we can just plug this into a calculator, and that's what I am going to do. 0.4 times the square root of x. I'm using x instead of t because it's just easier for me. Times cosine 0.06x dx. And this is equal to approximately 2.043, and we add this to 20 here. So 71 plus this plus 71, which is so it's approximately 73.043 degrees Fahrenheit. Obviously, you need to write a little more, so we're gonna just say by FTC, the change in temperature is the integral from 0 to 25. Sorry, I didn't write this down because I'm not used to writing it down and speaking, but by speaking, I hope I can give you guys a general sense, a general idea of what you guys should be writing down. I'll try my best to remember, but I'm sorry, I was a little short on time. So, okay, part two. So we just forget about what we did in the previous problem. For t is greater than 0, a particle is moving along a curve at the position at time t, x, t, y, t. At time t equals 2, the particle is at position 1, 5. It is known that dx over dt is this, and dy over dt is sine squared t. Okay, part A. Is the horizontal movement of the particle to the left or to the right at time t equals 2? Explain an answer. Find the slope of the path of the particle at time t equals 2. So, the horizontal movement of the particle is given by x t, x prime t. If x prime t is less than 0, it's to the left. If x prime t is greater than 0, it's to the right. Alright. Alright. So, you guys probably can't read this. If you can, I salute you. But, um, yeah. So, if times equals 2, what is the derivative? Well, we can just plug in the calculator. We click math underneath alpha. Instead of going to 9, which is f and int, we go to number 8, which is n deriv, and we take the derivative with respect to x. Well, it should be with respect to t, but again, I'm always using x because it's just easier for me. Of the square root of x plus 2. Oops, I don't know what I did there. Sorry. The square root of x plus 2 divided by e to the power of x. And when x equals 2. So this is, so we convert down. So the dx of d over tt, sorry, of t squared is approximately negative 0.236, which is less than 0. So it moves to the left. Now it also asks you for the slope. I'm not sure why it does that. I feel like it should be in a separate problem, but sure. The slope is, well, the slope is just dy over dx, but this is equal to dy over dt over dx over dt, which is approximately equal to, well, now we can just plug this into the calculator again. Okay, sorry. I think they want you to actually write out the values here. So dx over dt of sine squared t when x equals when t equals 2 over d, sorry, there's t, d over dt of t, the square root of t plus 2 over e to the power of t when t equals to 2, which is approximately equal to, well, let's calculate the top first. D over dx of sine x squared when x equals to 2, negative 0.7568 divided by d over dx of the square root of x plus 2 over e to the power of x when x equals 2, which is approximately, well, we already calculated this, but let's just do it again for fun. Divided. So we take negative 0.7568 divided by the bottom, and this is approximately equal to 3.195. Okay. Be sure to circle your answers. I'm sorry, I'm telling you guys a lot of stuff in the middle, but that's not yeah, I'm just, in case I forgot, I just forgot at the beginning. I'm sorry. Uh, Find the x coordinate of the particle's position at time t equals 4. Well, we're given the position at 1 at times t equals 2, which is 1 comma 5. So we want to know how much it moved between times t equals 2 and t equals 4. Again, this is the fundamental theorem of calculus. It's your best friend, especially in calculus BC. So it'd be the integral from 2 to 4 of, it's the x coordinate, so it'd be the square root of t plus 2 over et, okay, sorry, by ftc, the change in x between t equals 2 and t equals 4 is this here, dt, uh, which is approximately, I'm going to use a calculator here, from 2 to 4 of the square root of x plus 2 divided by e to the power of x dx is approximately equal to 0.2529. We only need 3 sig figs, so 0.252. And then we add 1 at t equals 2, the x equals 1. So at t equals 4, x equals 1 plus this, the integral here, which is equal to 1 plus 0.252, which is approximately equal to this, which is approximately equal to 1.252. Alright, find the speed of the particle at times t equals 4. Find the acceleration vector of the particle at time t equals 4. Okay, the speed of the particle. Well, there are a few ways to do this. One way is just, okay, I mean, both of them reach the same answer, but I feel like the more intuitive way to think about it is if we find the, how do I say it? If we find the derivative, the x derivative, and we find the y derivative, the speed is just, okay, let's say this is the x derivative and this is the y derivative. The speed is just the hypotenuse here. Because it's pretty much just the arc length, right? So I'm not sure if that makes, sorry, I'm not sure if that makes sense, but um, yeah. So okay, it'd be dx over dt squared plus dy over dt squared. So this should look more familiar. It's the integrand for arc length. So yeah, so intuitively it makes sense. So if we look up here, dx over dt is equal to, okay, I just realized that dx over dt is uh yeah, so here I wrote the derivative of this has to be less than 0, but it's just the value here. So um sorry about that. I am not, so I should restart this over here. So when t equals 2, dx over dt is the square root of 2 plus 2 over e to the power of 2, which is equal to 2 over e to the power of 2, which is greater than 0. So it's to the right, not the left. And here we have, instead of this, we have sine squared 2 and 2 over the e to the power of 2, which is sine of 2 squared divided by 2 times e to the power of 2, which is, sorry, which is approximately 3.054. Sorry about that. I completely messed up. But now we can finally move on here. When t equals 4, okay, we have, oops, x prime t is, where is it, sorry. X prime t is square root of t plus 2 over e to the power of t, and y prime is equal to sine squared t, right? So the speed is just, okay, I don't know how I got down here. This is just dx over dt squared. This is just square root of 4 over e to the power of e squared. Sorry, t equals 4. So square root of 6 over e to the power of 6 squared plus um, sine squared 6 squared. Sorry, sine squared 6, sine squared 6 squared. Okay, and then we just plug this into calculator. So square root of the square root of 6 divided by e to the power of 6 squared plus sine of 6 squared squared. And this is approximately equal to 0.078. Yeah, so yeah, and so the speed is this. So this is one part, and the acceleration vector. Well, it's just this, except it's this, but differentiated. So we have d squared x dx dt when t is equal to 4 squared plus d squared y over dt squared when t equals to 4 squared. Well, now we just use a calculator here. So it's approximately equal to the square root of the derivative of, with respect to x, of the square root of x plus 2 divided by e to the power of x when x equals to 6 squared, sorry, let me, squared plus the derivative sorry, with respect to x of sine of x squared d when x equals to 6 squared finally, and this is approximately equal to 0.536. Alright, final part. I hope, yes. Find the distance traveled by a particle from t equals 2 to t equals 4. So, it's asking you for the distance traveled, um, not the total distance from the origin. So, this suggests the use of arc length. So, recall, okay, I don't know what happened again. My page keeps moving around, I'm sorry. Recall that the arc length is calculated as the integral from a to b of the square root of dx over dt squared plus dy over dt squared dt, right? Well, okay, sorry. So the arc length is the integral from 2 to 4 in this case, plus the square root of dx over dt squared plus dy over dt squared dt. And d and this is equal to the integral from 2 to 4 of the square root of t plus 2, the square root of t plus 2 over e to the power of t squared plus sine squared t squared dt. And then we can just use a calculator again. The integral from 2 to 4 of the square root of the square root of x plus 2 divided by e to the power of x squared plus sine x to the power of 4 dx. And this is approximately equal to 0.65. Yeah, 0, 3, yeah. So, that's how the time's going, and that is not my clock. We have approximately 5 minutes left. So, I don't know why that keeps pulling up, I'm sorry. But now we can go back and check our answers for 5 minutes. Or actually, we should circle our answers, because that is what we should be doing. So, circle answers here, and circle answer here, underestimate, and we have here the change in temperature, and here. Yeah, so, but yeah, I mean, I'm to check your answers, I'd suggest just redoing these problems, if you have enough time. If you have like 4 or 3 minutes like me, not enough time, I'd say just, just skim through the problems real quickly. Go back to ones that you're not too sure on. But yeah. So as a recap, as I did this problem, and as I did these problems, um, first of all, they like to throw a curveball at you, right? They might not always give you, like in the second part here, they might not give you the I can find it. They might not give you the position um function right up. They may throw a curveball at you, right? They may give you, as in this case, the derivative of the position function, which caught me off guard, and I spent a lot of time having to go back and correct everything. So make sure you look out for that one too. Make sure you look out for that. Um, but other than that, I don't think I hit many roadblocks. If your theory is solid, you shouldn't have much of a problem outside of mistakes like me. And really, the only way to minimize mistakes is to just take practice tests to get a feel for it. But other than that, I don't have much, many tips because, who am I to talk about minimizing mistakes when I mean like 5 mistakes already? So, but yeah, that's a general idea. You don't you don't really need to manage your time as well because you have 2 problems and 30 minutes, but make sure you don't spend as much time on each problem as possible. It's not as time intensive as the MCQ, but you still need to manage your time. So that's all I have for uh, section 1 of the free response. So yeah.